In this question, we're considering a sphere that falls from rest through the air. The graph shows the variation with time of the sphere's velocity. And so students that have studied this physics will recognize that this object is increasing its velocity from 0. The slope of the velocity time graph gives acceleration, and the acceleration here would be just the acceleration due to gravity. The weight of the person would be the force that makes them accelerate. Okay, so initially you'd have B. We're trying to solve for the diagram that shows the forces acting on the sphere when it is at the velocity corresponding to point P on the graph. And so initially there's weight and weight alone. That would be choice B. If the point were sort of like here, then B would be the correct answer. By the time we're at point P, we've given the wind a chance to act on the object. And so the air resistance becomes more and more pronounced until eventually it's equal to the weight. And that's at a special speed that we call terminal velocity. So you can see that the velocity is approaching some sort of top speed. And at that point, where the slope goes to 0, there is 0 acceleration because the forces are equal. And so if point P were somewhere over here, then we could say A would be the correct answer because air resistance and weight are equal. Well, what happens in between here and here? Point P and choice C, which is the correct answer, right? The air resistance isn't quite equal to weight. So it's still sort of, the slope is getting more and more shallow until eventually it is 0, where agreeing with the force vectors in choice A. Choice D looks like the air resistance is greater than weight, and that would be if this weren't a sphere, but a parachutist that eventually deployed a parachute, there'd be a net force acting up, decelerating the object, right, to a safer landing speed. So don't forget about the physics of skydive. This has been another worked example with Dr. Schleck. We'll see you next time.